Thank you. Nadav, to you.
Hello, good morning. I'm Nadav. Yesterday, Snir gave us an introduction about condensed matter and specifically about quantum systems which are coupled to the environment.
Nadav, speak closer to the mic.
Is that better?
Yes.
Okay. So, Snir gave us an introduction about quantum systems which are coupled to the environment. And I will use this framework to talk about memory. Usually when we talk about error correction, we rely on active protection. We do some measurement and then some procedure of correction. But in self-correction, we care about physical systems that retain their memory naturally. Their intrinsic physics somehow retain the information. And specifically in this talk, we'll discuss the specific quantum case of toric code, and we'll see and understand why the 2D toric code fails to be self-correcting, and the 4D toric code is self-correcting. So we'll start by giving a definition of self-correction, mainly classically. We'll move to talk about thermal dynamics and detailed balance, as also Snir talked yesterday. We'll give a classical example of self-correction through the Ising model, as we like. And we'll see that the 1D Ising model and 2D Ising model are very different. While the 1D Ising model is not self-correcting, the 2D case is. We'll then move to some abstraction to try to understand these models through chain complexes. And we'll use this understanding of chain complexes to also examine the toric code, and then we'll understand why the 2D case is not self-correcting while the 4D case is. So what is self-correction classically? We have a system with different configurations, and we encode a logical qubit on the ground space of the system, which is described by a Hamiltonian, a classical bit. Yeah. Now, everything now will be classical. When we move to the quantum case, I will say it explicitly. Oh, sorry, okay. Correct. And we let the system evolve naturally. We'll say what is naturally, and ask whether it stays somewhere close to the initial code word in a way that we can somehow know what was the initial code word. Then we ask, does the state of the system at time t still belong to the original logical state? And we ask what is the scaling of this time as a function of the system size L. And we typically want this time to be exponential in L. If we want to be more formal, so L is the system size. When we will have a physical example, it will be more concrete, like the number of bits. And I will now define formally what is T. So given the configuration space of the system and some mapping, we map every configuration to some logical state. We can think of it as a coloring map. Each state of the system could be 0 or 1. And we have some initial configuration of the state, sigma I, which we map to the logical state I. We have then a stochastic process on the system. It evolves stochastically in time. And then we care about the memory time is what is the first time in which the logical state is flipped. What is the first time that the value of f won't be I? And we will omit this tau I, like the I of tau, because we just assume that it's the same for both cases. Questions so far? Yes. I think it will be more clear when I talk about physical systems. Okay, then we move now to thermodynamics. I said that it's a dynamical property. We have some stochastic process on the system, so we have to specify what's the dynamics. So as Snir said yesterday, we can model the dynamics or the noise on the system by coupling the system to a thermal bath. We assume about this thermal bath that it is large, it's memoryless, it's inaccessible to us. We cannot know things about the bath. We cannot measure it. We can just know its temperature, which I will talk about later. But importantly, the bath and the system exchange energy. And because of that, the energy in the system is not fixed. Formally, all these assumptions induce continuous time Markov process and configurations, and we'll make it formal in the next slide. And also physically, it means that we'll have local operations which are spin flips, or in the quantum case later, single Pauli errors and different qubits at a time. So we can think of the Markov process as a graph in which the vertices are different configurations of the system, and the probability currents between them is the dynamics. After a long time, the system reaches a stationary distribution, which is the Gibbs state. And the probability to be in each configuration is proportional, as we saw yesterday, to the Gibbs weight, which is weighted exponentially with the energy. And beta is the inverse temperature. If we take the limits, when we have large temperature, which means beta goes to 0, we get a uniform distribution, and when the temperature is low and beta is very large, we're concentrated around low energy states. For the scope of our talk now, it's good to think of energy as just the number of violations. The Hamiltonian assigns energy to a configuration, which is the price of the cost of a specific configuration. And in this context also, it's, the Hamiltonian does not do anything to the dynamics. In the quantum version of the Gibbs distribution, we'll have the Gibbs density matrix. And we also know that in this case, we have detailed balance, which graphically here means that the net current of each edge here is 0. Why is detailed balance important for our discussion? Because we don't care only about the stationary distribution, because once we reach the equilibrium, we actually lose our initial information. So what we care about is the dynamics, what happens, sorry. We want to know what happens before we reach equilibrium and how much time it takes us to get there, how much time we retain our initial information before we get to the Gibbs distribution. But using detailed balance and the Gibbs distribution, we can infer properties of W, which is the transition rate matrix.
Nadav, before you move to the, can you go back to the previous slide? You said you assume detailed, in this case you assume detailed balance. What do you mean? So you said in this case we know detailed balance holds. Basically what you mean is that
when we couple a thermal bath under these assumptions, we know the detailed balance holds.
these assumptions mean that you have only a single bath, right? I'm sorry?
But
No, detailed
detailed
balance and
balance is
stationary
also-
is not the same. It's not the
it
same,
holds
that's why I'm
also
asking.
before we reach the stationarity.
And also detailed balance, I mean, you can have stationary systems in which detailed balance does not hold. For example, fault-tolerant quantum computation.
We can
Is
have a steady
something like
state
that.
which is not
So, so there are basically two different. Wait a moment. Wait a moment, just a second. I opened a can of worms. There are sort of two different settings, and we're now talking about the simple setting. Okay, the simple setting is where you have detailed balance, there is a bath, and that due to the interaction with a single bath, you assume basically that this detailed balance holds, or with
No,
a
I
single
think that
bath you
under
know
the-
that.
under the assumptions of the bath that we mentioned, we can show that.
Right,
detailed
okay.
balance.
So we now assume from now on in this talk, and basically, I think throughout the day, the detailed balance holds. Wait,
Not tell us when it occurred, but just how to think about it. What does it mean, say, if we are performing random walks or Markov chain? How to think about
so I think Nadav can
I
say,
think
but
the important point about detailed balance for us is this, is when we use detailed balance as stated here, and the Gibbs distribution as the stationary, it tells us something about the ratio between transition rate.
yeah, so it basically tells us something about how the system approaches equilibrium. What is the dynamics?
So now this means that if we have some energy landscape of our system, which assigns the energy for each configuration, when we jump between configurations, going uphill to higher energy will be always suppressed exponentially, assuming we're in low temperature. Without this, we can have the energy landscape, but it has no dynamical meaning. So with the energy cost and the detailed balance, we get some condition on the rates, the ratio. So it's also interesting to see that the noise, which like everything, all our dynamics is from our bath. It's the source of our noise, but it's also the correction mechanism, just by the tendency to go downhill and not uphill according to the energy. It's also interesting and important to mention that it's a strong assumption about the noise if we consider depolarizing noise, in which we just we get a mixed bit with a probability p, and this is agnostic of the energy. It just changes the bit and doesn't care about the energy. This is like saying we have infinite temperature. And because of that, for any depolarizing noise, we won't have self-correction in this meaning of a thermal bath. Questions so far? Yes.
Okay. So you are saying that the detailed balance defines you the transitions probability for the Markov chain.
Yes.
But you are interested in the case where you're still not in the Gibbs state about the memory of the system. So
Yes, we started with some initial state, which is not the Gibbs state. And then we let the system evolve according to this Markov chain.
But the transition probabilities chain are not the same when you are not in the Gibbs state.
No, the transition rate will be always the same, even though like it's not a condition. Detailed balance is not a condition about the stationary case. It's always from the beginning of the dynamics.
But in order to get the difference between the rates, you had to plug in the Gibbs state.
Yes, but the detailed balance here, P is the stationary. It's a condition about the stationary distribution. But W is fixed in time. It's true always.
Okay.
It basically says that somehow the system knows where it's going to. Okay? It says that not globally, but the system knows whether it wants to increase energy or decrease energy. And the increase and decrease energy is a local thing. By a change of bit, you can basically, the system can calculate locally what will be the change of energy. Of course, it doesn't do it like that, but it is, I mean, in theory, in spirit, it can calculate what's the energy of the new configuration, what's the energy of the old configuration, and it decides whether to go up or down according to the probability e to the minus beta. Okay?
Yes. Yes. So, in the polarizing noise, the change we do, the error, does not care about the energy result. Like here, we say that each transition checks what's the resulting configuration, and according to the energy, decides whether it does this transition. The polarizing noise is agnostic. It does the noise. So it's like we don't care about the energy at all, which is like infinite temperature. That the ratio here is 1. So after we understood a bit about thermal dynamics, we'll now move to a classical self-correction example in the Ising model. And we'll see that self-correction with thermal dynamics requires a macroscopic energy cost, which means that the cost grows with the error. And we'll see that in the 1D Ising model, violations are point-like, which means that we pay only a fixed energy cost for a large error, while in the 2D case, violations are loop-like, which means that the cost grows with the error. And in that case, we will have self-correction.
In a temperature below some threshold.
Yes, below some temperature. So the Ising model, we have spins, which could be minus plus 1, on some lattice in 1D or 2D, with local interaction of neighbors. Spins want to align with their neighbors. And we can think of this also as a repetition code, and the Hamiltonian, which assigns the cost, is analogous to the check metrics. And the violation of checks is like the energetic cost from the Hamiltonian. Our logical would be the majority, or like the mean spin, which we call magnetization in physics. And under this thermal noise that we presented, each spin may independently flip with some rate. We can think of it as having many Poissonian clocks on each spin. And they choose whether they flip according to the detailed balance. This is similar to metropolis dynamics. Is the model clear? Questions? Okay. So let's start with the the 1D case. We start with spins sitting on a chain, and we initially set them all pointing up. And we have some energy for this, which is the ground state energy. And we ask now what's the cost of flipping some minority. We take some spins and flip them down. What's the cost of having this kind of error? We see that it's according to the, we have only two variations, these two red dots. And the cost is 4J, according to the Hamiltonian. Is there a question? Okay. Why? So for two aligned spins, we have minus J. Anti-aligned, we get a J. So the difference of the creation of this anti-alignment adds 2J because we have two boundaries, two red dots, we get 4J. So that's the cost of the creation of this minority. And now we ask, what's the cost of expanding this string, of taking this down minority and make it larger? And we see that there's no additional cost. Moving the boundaries doesn't change the energy because we just moved the anti-alignment, but the minority here doesn't care about what happens inside, only in the boundary. And we can expand it more and more and enlarge the arrow, and we don't pay any other cost. In the language of detailed balance, it means that once we had some error, the creation of these boundaries, the boundaries can walk without any cost, and they do just a random walk. It means that once some very small error has occurred, there's no mechanism that takes us back. They just walk around, they can expand the string, they can make it smaller, but there's no going downhill. It's all the same energy. And now we can ask, what's the time of the memory of this 1D system? So we can think of a very large system, a long 1D-izing chain. After some time, we'll have many such pairs with density, such domains, pairs I mean pairs of organization. And the density of these minorities would be according to the probability of their creation, which is according to the initial cost of their creation. We said that the cost is 4J per minority. So the probability of their creation would be exponentially with this, will be exponentially small with this cost. But once they're created, now they can, as I said, they can just move around.
It's not quite accurate, correctly. So it was when the last simple one flips, you actually gain. There is a hole of one. That child flips,
I don't understand, sorry.
Think of a situation where this hole is just a single bit, and it flips to be correct. Then you're gaining 4J.
Yeah, but nothing corrects us. It could be, like I said, the
But
string,
chance, no,
Yeah, there is a
it's a random
yeah.
walk with an absorbing wall.
but there's no correction mechanism.
No.
Okay.
But chance can be on your side as well.
Yes.
Okay.
And then we have a typical distance between them of this psi, according to the density. They do a random walk, and minority would take over just when these boundaries would meet. And this time of meeting does not depend on the system size, generally. And it, like we know from random walk, it would just take psi squared time until these boundaries would meet, and we have no memory because it does not depend on the system size. We can make the system bigger, but it doesn't improve our time. Questions about
Nati,
that?
do you want to expand on this? So this can be made rigorous. It's
Yeah,
not
it
a
could
rigorous
be,
argument.
yes. Okay. We move now to the 2D Ising case. And now instead of having a chain, we have a lattice and a torus. And spins here would sit on plaquettes. We create a minority domain, an arrow, and we ask what's the cost we pay now. And we see that the cost is very different here because we pay for the parameter. Each of these red edges are a cost we need to pay because the neighboring spins are not aligned. And if we expand this arrow, we need to pay more according to the parameter of this arrow. We also notice that for a failure to change our logical, the mean magnetization, we must pass through a configuration of a macroscopic domain, a large arrow domain which is comparable to the size of the system.
Sorry, can you say that again? What did you say?
Our logical is the mean magnetization, which is the mean spin. When does this change sign? When we have majority of an arrow. And this means we have an arrow which is comparable to the system size, a very large gray domain.
Yeah, you're saying that in order to move from the all up to the all down, you have to create some configuration during somewhere in the middle where there is at least whatever the energy you're
Yes.
right, but you meant didn't you actually want to say that that not only that the number of downs will be macroscopic, but also that the boundary will be macroscopic.
That's correct. If we
That's the point.
that's the point. When we have a large domain of down, we will also have to pay a very large cost, which is proportional to the parameter of this domain.
Yeah, because this is the difference between 2D.
Yes. So now we want to calculate the memory time. We pick some specific macroscopic size loop lambda. And according to detailed balance, we know that the rate of this creation of a large loop moving from a small initial loop, a small initial error to a large error is highly suppressed. We can think of it as many steps we need to do, and each step is suppressed with minus beta j. And we have to, going to a specific loop requires many of these suppressed steps, and because of that, the rate of the creation of a specific loop lambda, which is large, is suppressed like exponential of beta j L, which is the system size. But the problem is that that's for a specific lambda, a specific loop. But here, we also need to consider the entropy. While the configuration of all up or all down is, we have only a single configuration like this, we can have many different configurations with large loops in the system. This is like the entropy of loops, the log of the number of loops. So we need to take the rate, but also weight it with all the possible, the number of all possible large loops in the system. We can bound this number with mu to the L, where mu is some constant around 3, which depends on the lattice, and L is the length of the loop. This is called parallel argument. The idea is that we can just count the number of strings of length L, and closed loops with length L are a special case, so we can bound it from above with this boundary. Questions? Yes? Okay, so we want to ask, in the 2D Ising case, how much time it takes for a failure. And we know that for a failure, we have to pass through a configuration with a large error. And we know that a large error means large parameter of the error, and we have to pay a high energetic cost for this. Okay. And we know, according to detailed balance, that this energy cost comes in the rate. What's the probability for doing these steps that cost us energy? Because the cost is very large, the rate is very suppressed. So that we know for a specific configuration, a specific loop. Okay, for some loop with size L, that's the rate of its creation. But now we need to account for all possible large loops that we can end with. Okay, and that's the entropy of the loops. So if we weight the rate, we have this expression where the green part is the entropy of the loops, and the purple is the energetic suppression. And if we think of it as forces, the energetic suppression tries to shrink our domains, while the entropy tries to expand them. We can infer from this the memory time, and we see that we can write it as the exponent not of the energy, but the free energy. And when I say free energy here, it's a bit abuse of notation, because free energy is a property of the system, not of a configuration. But here we define something like free energy of a system with loops with size L.
Sorry.
Not very important.
Is it important because
No.
if okay.
Let's move on. But it's a technicality.
Probably you will know the answer, but actually the
Yes, yes. The entropy is the log of this. Yes. Yes. So we see from this that there's a critical value of a critical temperature for which the free energy is below this critical temperature. The free energy is positive, and the time grows exponentially. But above this temperature, the entropy is more important than the energetic cost, and we have no memory. Okay,
What
because
is, sorry, I'm confused. What is E of L?
E of L is the energetic cost of a loop of size L.
Okay, and what is the entropy of L?
It's the log of number of loops of
That size.
of that size.
Okay, so you're talking about the free energy not of a particular loop, but of
It's a,
all
a, a
all
macro,
loops
a macro
of a
state,
particular okay.
a macro
of a
state
certain
which
size.
is, yeah, all the states with a loop of size L.
Okay, so you're defining this property like the free energy of all of the set of loops of that size is the energy which is defined by that size minus t times the log of their number.
Yes.
Okay. And you're saying that this is the main value that determines the whether there will be memory or not.
Yeah, it's not only important to have energy cost. We also have to be in a low enough temperature, so the energetic cost is more important than the entropy. Yes.
I'm not sure why you count the number of loops, so it looks very similar to Paris' argument.
It is parallel.
Yeah, that's what I
okay.
was alluding to. But the Paris argument talks about a statistical ensemble, so you sort of count the number of configuration in a steady state. For this to fail as a memory, you just need one instance for it to happen. You need, a single loop will involve. You don't need to sort of sum an ensemble of loops. I don't understand. You ask a very different question. It's not about the sum over all configurations. You need one trajectory that would kill your memory, right?
Yes, so I weight all the possible trajectories. I count possible paths. That's why I started.
Yes, what's the time? Yeah. You don't need to have all of them occur.
No.
Yeah.
But the number of ways.
It's like coarse grain.
Yes, yes. The number of ways will affect the time because if you have many ways, then one of them will happen in a much shorter time. Yes, that's the proportionality.
So two mathematical comments on this. First of all, there is such an area called counting lattice animals, which is exactly what you do here. And it's known to have a constant, but they don't really know it. So this is only if you really want to understand whether, as a qualitative argument, there is no problem. But if you want to make it more accurate and really find out parameters, then you don't even take into account the shape of this, which of course determines how large the boundary is. Right? The area and the boundary do not necessarily define each other.
Yes.
So you also have to understand, to make this really accurate, you have to understand what the typical shape of this gray area is.
Yes, of course. Yes. Like when we say that the cost is according to the parameter, it's not because we're on a lattice. It's more subtle than that. But qualitatively, it behaves.
No.
like
It's a qualitative argument. I have
Yeah.
no problem with it. But if you really want to make it quantitative, you'll have to sweat more.
Yes.
No, but the lattice animals and the geometry of the
Another question.
Can you give more of the high level, big picture? Why do we analyze this? Understood we analyze how it evolves over time, such errors, but why do we care about it?
So this Ising model is a classical example of two systems, and for which we checked whether they remember, whether they have memory. We started from some initial configuration. We assigned a logical bit for the configuration, and we asked whether we stay there over time. And in the 1D case, we saw that it changes the logical bit quite fast, and here in the Ising model, we will remain in the same logical. Okay, that's the classical example. We move on to the quantum case. Yes.
So this model, the two-dimensional Ising model, also has a phase transition at a finite temperature. And the argument seems very similar to the one you are saying.
Yes.
So is it the same, or is it a different story? Because I could say, if I have phase transition, I say, let's say I'm the ferromagnetic phase, so I know that there are two states, one up and one down, so presumably if you start mostly down, you will remain always mostly down. If you remain...
In the Ising model, it is the same, but I don't know, like, I don't know if it's something general, whether phase transition and memory is the same.
I would say that spontaneous symmetry breaking means that you keep one sector and you stay there forever. That's the
Yes.
definition of spontaneous symmetry. So whenever you have spontaneous symmetry breaking, it also means that you have an infinite time constant.
Where is Tal? Ah, here you are. Do you want to make a comment on this? Huh? You could?
I think there are two subtleties or two levels in which we're talking. When we're talking about infinite systems, then when we have ergodicity and two different external measures, then we are locked forever in two different configurations. When the systems are finite, then we're always converging to the Gibbs measure, and there's supposed to be some, at least in the 2D Ising model, there is a connection between the lack of ergodicity and phase transition, namely, and memory. So, if it says anything.
So what
But
physicists believe, and if you have a counterexample that was previously, is that when you have spontaneous symmetry breaking and a finite system, then if you wait infinite amount of time, everything will flip, but it will take exponentially long time. So the question is whether you can construct a model that in infinite size has spontaneous symmetry breaking and in finite size flips in a time which is less than exponential.
yes, I think mathematically it's not completely closed. Martinelli is one of the main players in this, but I think that in many cases it is known, the connection.
I guess there is no known counterexample.
Yes.
So what we know so far from the example we saw on the Ising model is that the geometry of excitation, whether we have, or the violations, whether we have point-like violations or we have loops, that dictates the energetic costs of error, whether it grows with the error or is it fixed. And we also saw that thermal dynamics or Dieter balance is what connects this energetic cost to the dynamics. And in the case of loop excitation, below some temperature, critical temperature, the energy costs of loop is larger than the entropy, and then we get memory. But now we'll go out of these examples and try to generalize this and ask for which Hamiltonians, similar Hamiltonians to the Ising model, but also in the quantum case, when do we get excitations which are loops, and when do we get only point-like violations?
So maybe
Yes.
before you move to that, just to make to clarify this point of connection between the phase transitions and memory. So memory is about a finite system, and how long it can remember its original state. And phase transitions is in the thermodynamic limit, and there is a very, very, very tight connection between the two, but it's not exactly the same.
In experiments, it always experiments of finite time.
I know.
But the transition temperature is exactly the same. I mean, the temperature, the critical temperature that you're talking about, right,
In this
is exactly
item
the same as the thermodynamic transition.
So now we move to do some abstraction and use question.
I have a confusion. Maybe it's because I need the definition of the entropy. So the question is, you can have a loop of a length L, and then you can have a separate loop somewhere else with length L. It has the same energy. So that's one type of thing you can have. Or you can have like a wiggling of the shape of the loop that preserves the length. So all these things have the same energy, but you don't expect the transition rate between them. Like by detailed balance, it's the same. Maybe the definition of the entropy that I don't know makes one of them more favorable. What is the...
Yes,
yep.
So that's a subtlety that we don't care about now, but generally it behaves the same.
Yeah, that's
take
what
into
Nati
account-
was explaining, that one can actually look at this various shapes, etc., but and can make this argument rigorous, but this will not be done here.
And what is the definition? It's trace roll and roll. What is the definition of the entropy for this problem?
So because any loop with size L has the same energy, they all have the same probability, and weighted with the energy. So we just can treat the entropy as the multiplicity, the number of loops, log number of loops. Okay, so moving on to chain complexes. So the definition for our scope would be a sequence of vector spaces with boundary maps between them. And because they are boundary maps, they satisfy the fact that a boundary is 0. So VK is an F2 vector space generated by K cells, where K is that dimension. A 2 cell would be a plaquette, a 1 cell would be an edge, a 0 cell would be a vertex.
Nadav, maybe you can put it on the board so that...
I will have like this.
okay.
Do we still need the board? No. Okay.
We will need it in front of our eyes throughout the
We'll
next...
have it.
Okay.
In the next slide. And a K chain is a 0-1 vector indicating which K cell is present. So in this example, we have here a plaquette which is triggered, and we assign a 1 to the in this vector. We have an entry for each plaquette, and this gray plaquette is triggered, which means it has a 1. When we apply the boundary map on this vector, we will get the boundaries of the triggered plaquette, and this gives us these 4 edges. And when we apply again a boundary map delta 1, we get zeros because it has no boundaries. This is because it's a module 2, and each vertex is counted twice for each edge, so we have 0. Questions about this? Yes.
If it was,
I
let's
can
say,
hear
in the okay, if it was a different example, and the gray in V2 would be in the edge, it will be different.
In the edge, you mean here?
Yeah.
We assume it's an toric, so there's no edge,
Okay.
there's no boundary. One. Okay, so now we're going to use this idea of chain complexes to rewrite our Ising models. So we had this Hamiltonian of the 1D Ising of neighboring spins, and now we rewrite this as a sum of products according to the co-boundary mapping. Okay, this means that we have in the Ising model and the 1D lattice, neighboring sites are just according to to this boundary. Okay, do you
No,
see
it
why is
wasn't
that?
clear.
Okay, so let's. So we have here.
What is the claim?
So that we can write the Hamiltonian of our 1D Ising model just with a chain, a chain complex.
What does it mean to write it as a chain complex?
It's just it's the same. Just how did we define the neighbor? We can just know it from the boundary. Let's sorry. Go ahead.
You haven't defined delta 1 T. That's it's a good idea to do this. Delta 1 super.
So delta 1 T is
This is the co-boundary?
yes, it's the compound. It's that it just it's the inverse. It gives us
So where does it start from? Where does it go? And what does it give?
so if we have a bit on an edge, delta 1 gives us the two vertices that touch this spin. Okay? But now if we ask about a check here which lives on a vertex, and we ask what spins touch this check, this is given by delta 1 T. It gives us this and this. Yeah, maybe a different formula.
So delta 1 of a vertex is the sum of the edges that touch it? Delta 1 of a vertex is the sum of the edges that touch it? Delta 1 T.
Delta 1 T for a specific vertex gives us the edges that touch. Yes. So if we want to write the 1D Ising model, it just means that we take a vertex, we take a check, and with delta 1 T, we get the spin that touches this check and take their product. Okay? That's what we say here. It's the same as the original Hamiltonian, we just write it with the boundary map or co-boundary map in this case. Okay? Yes.
Just as a numerical calculation would, I mean, assuming that not everyone is completely at home with homology and cohomology and everything, mathematically speaking, what you do here is rather, I mean, if you just want to understand this equation, it's just reversing the order of summation, that's all. Rather than summing according to edges, you sum according to vertices and make sure that you count everything the right number of times.
Yes.
If you just want to understand this equation, this is all what's going on. Without the background, you don't need, you know, it's very good to have the background, but you don't need the background to understand this
No,
equality.
but now we're going to use, like, that's a simple example. This means that if we have a configuration of spins which lives in V1, which means that we have, let's say, 1 for each spin up and 0 for spins down. When we apply delta 1 on this configuration, we get all the triggered checks, all the violations. Okay, they will be ones for every violated check. These are what we had vertices in the 1D case.
Okay. And checks are bits, are vertices.
Checks are vertices. We can do a similar thing with the 2D Ising, but now we promote the rolls. We put the bits on the plaquettes and the checks on the edges. Why is that? If we take the co-boundary of an edge, we get 2 spins and take the product. That's the same as written in the 2D Ising model of interaction between neighboring spins. So again, we write the 2D Ising model with this boundary map. A configuration lives in V2, and when we apply delta 2, we get all the violated checks of this configuration.
Sorry. So a check here is an edge, and for each edge you take the product of the
neighboring spins.
which are now vertices.
Okay.
I mean, which are now plaquettes. Okay.
So 1 is the degree and minus 1 is the DC.
Yes.
This exactly takes care of who's on the boundary.
Yes, when we introduced the Ising model, we said that it's an interaction between neighbors. What it actually means that, like, these deltas, the boundary maps, are the one defining who are the neighbors. But now something interesting happened. We have another vector space of the vertices that does not appear in the Hamiltonian, but it creates an important geometric constraint. We know that delta 1, delta 2 is 0.
What is this M there? Okay.
Why? Because I decided.
So just what happened here is that you now want, by your definition, to describe the 2D Ising model where the checks are that the spins, each 2 neighboring spins are the same. You now want to represent it as in the language of chain complex.
Yes.
So you decided to put the spins on the plaquettes instead of on the edges.
No. In the 2D Ising model, before also it was the same.
Yeah, but this is an arbitrary decision.
We can put it on. It's not quite arbitrary. It is important, and that would be my point here.
Yeah, but before in the 1D case, the spins were on the edges. Now they're on the plaquettes.
Yes, because there are different models, but it's the same model that we had at the beginning of the talk. We only write it with the chain complex language. But also before we had bits sitting on the plaquettes, and in the 1D case we had bits sitting on the edges.
You don't sketch on the computational system.
Yeah.
Now on the plaquette.
Yes.
So we just moved from to the dual graph, like the original Ising model. So you moved from, like, originally the Ising model here, it doesn't matter if you are working with the vertices or the plaquettes because each graph is
Yes.
dual to each other, but it's only for the square lattice. So like here you can do it freely and not worry about it, but
We care only about the square lattice.
okay,
here.
but
Okay, so as I started to say, now that we are in 2D and we put the bits here and the checks here, we get another vector space in the chain complex of the vertices, which has no role in the Hamiltonian, but it is very important because it causes a geometric constraint. As I said before, because the boundary of a boundary is 0, delta 1, delta 2 is 0, this means that for any violated check configuration delta 2m, when we apply delta 1 on it, we'll always get 0. This means that for any configuration of violated checks, they are all loops. They have no boundary. Okay? When this means that, like, when we embed this on Euclidean space, any violated configuration will always come as a loop, while in the 1D Isaac case, when we had only a 2-chain, we had point-like violations.
This is, again, this is very, you know, I try to talk to the people for whom this language is foreign. What you're saying can also be understood completely elementary, things that you knew as kids. What describes the failures or the differences is exactly you had previously these pictures of the holes, the gray areas. And what you're counting now is just walking around it. And since this is a closed loop, you get 0 mod 2.
Yes, but
There can be 17 of them, doesn't matter. Each one contributes 0. So you can understand what I'm saying now is that these, if you want to understand what's going on, you can explain it to yourself in completely elementary terms.
Yes, but the important point, I do want to think of it in the abstract way, because when we move on to the toric code case, we'll see that the important point won't be which type of, what's the ambient dimension, in what dimension we live in, but what's the length of the chain complex.
Can you please write the bits in terms of the SI? Right?
Can you-
Formula for the bits in terms of the SI.
The bits in terms of the SI.
You know, the bits are associated with the plaquette.
Yes.
So how do you express the plaquette variable in terms of the SI?
It's equal.
The SI are sitting on the vertices.
SI are the bits. SI are the bits.
SI are sitting on the plaquettes.
And the plaquettes.
Then the checks, I don't know, but then the checks, but then the checks lie on the dual lattice.
Yes. On the edges.
Here you are confused, right? If the bits are sitting on the plaquettes, then the check don't lie on the vertices, on the edges of this graph, but on the edges of the dual graph.
No, on the edges of this graph.
No.
We are now talking about the toric code. We're talking about the Ising model, and the check is simply to check that this guy is equal to this guy, and for each edge you have such a check. Forget the chain complex. If you want to check that this guy is equal to this guy, each 2 plaquettes that are neighbors are separated by an edge, and you assign a check to each edge.
But this is confusing because
It is confusing.
because
נכון. Welcome.
because normally physicists, or I mean people who think simply, relate if you have spins here and there, then the interaction is the line connecting them.
But he
Nothing-
is deliberately
nothing
moving to a
blindly
different
dual.
language. Yossi is deliberately moving to a different
What?
language. Deliberately, he's moving to a different language.
We could have written this as bits here and just the dual of this, but this would be helpful later. Like I know usually we put them on vertices, but it will be helpful.
Oh, excuse me, maybe just a couple of words.
Wait, just a moment. I like this, Jim.
Thank you. Just a couple of words to your question. Actually, as for 1D case and for the 2D case, you can think just about the elements of partition. So you have a partition, all your space, yeah, is partitioned into some elements. And this checks is just the relation between between the elements of your partition. For 1D case, it is segments. For 2D case, it's plackets. So this checks is a relation between the elements of your partition. That's it. It's the same. Okay.
Okay, I think we are ready to move on.
Okay, but I want to express again the point here that once we have a longer chain, we have here 3 spaces, we get a geometrically a constraint, even though this V0 is not a part of the Hamiltonian.
So
And
delta 1 does not play a role in the Hamiltonian.
yes. It only means that any configuration of violated checks would be in the geometric form of loops. Oh, I have this. Now we move on to the quantum case. We want define precisely what's the meaning of quantum self-correction, but it's about the same idea. We start with a quantum state, and we want to retain the state for a long time. And we want to see how much time it takes when we move between logical words.
But it's not any quantum state like before, like in the Ising model. You start with the all zeros. Here we'll start from
With
a
a
state which is an
ground
an encoded state.
Yes. And we'll see that the 2D toric code is analogous to the 1D Ising model in the point of view of chain complexes, and that's why we don't have self-correction, while the 4D toric code is like the 2D case, 2D Ising case, and then we have self-correction. Let's go over the 2D toric code. I think it wasn't presented enough. So we have a Hamiltonian with two different types of terms of stabilizers. Stabilizers are a product of qubits according to this. We have z-checks, which are the BP terms. We take a plaquette and take the product, the z product of the 4 edges around the plaquette, and the A term, the X check, the X check is the product of the X of the 4 edges around a specific vertex. I feel like there's questions. Okay.
Maybe say out loud about the bits now on the edge.
Yes, in the toric code, in the 2D toric code, the qubits sit on the edges, and now we're in, I think it's written there, yes. And now it's qubits and not spins, not bits.
So it's like in the 1D Ising model where the
We
bits
still-
were sitting on the edges also.
I think it's confusing, so.
Okay, forget it.
But they sit on the edges, and each such B and A term is a stabilizer. It's a local parity check, and all of these stabilizer commute, also the A and the B terms, and the code space is when all checks are satisfied, which means they all have a value of 1. No. Spins are the red.
What do you mean the red? I don't know.
The
It's
red
not
one.
an edge and it's not a
No, on the edge. On the edge.
It says the spins are now on the edge.
Qubit sit on the edges.
Now the spins are on the edge.
Yes.
And in the picture on the right, what is
Same.
Always.
Always sit on the edge. It's the
And
same.
what is the dot in the picture on
the
the
check.
right? In the picture on the right.
That's the X check, which is the A term.
Okay. Good.
Okay, so we have two different terms in the Hamiltonian. The A terms, the X checks, and the B terms, which are the Z checks. We can think of them as the A's are sitting on vertices, that's why it's AV, and the B's sit on the plaquettes, that's why it's BP. Okay?
The qubits sit on the edge. Yossi, just a moment. Yossi, just a
Yes,
second.
but
Wait, just a second. Qubits sit on the edges. Okay? Now you add what Nadav calls checks, and for each vertex, for each plaquette, there is a check.
I was just confused because in the previous transparency, the bits were sitting
Right.
now they are sitting on the edge.
Right.
checks are stabilizer.
Checks is like the constraints we were talking about yesterday. It's basically checking that the space, that the state that we're talking about sits in some subspace. Meaning you force the state to have an eigenvalue 1 for those operators. Okay?
And a logical, which commutes with H but itself is not a check, will be a non-contractible loop, as we see here in the blue line, of Pauli operators around the torus. I don't think it's clear enough to read it.
No, it's not clear enough. Can you say it again?
So a logical operator of X or Z would be a string of Pauli operators that goes around the torus as in a non-contractible loop, like this blue string thing. I still don't think it's clear. Do you want to add maybe?
Well, I think we have said it in various ways, but we didn't actually say it exactly. Let me try, and then Nati will say it to the mathematicians. So the first thing that we can notice is that if we apply ZZZ on a code state, so that defines a code, as we all know. If we apply this thing, Z times Z times Z times Z, because it was defined as a state that is invariant under this, it doesn't change the state. But now we can apply Z times Z times Z times Z and again z times z times z times z, and again z times z times z times z, and z. So if we apply both this and this and this, this and then following by this and then following by this, these two z's on the edges cancel each other. So the result is basically applying a z along a boundary of, along a loop. And still this doesn't change the state, which means that the toric code state, any state in the code subspace stabilized by the stabilizers, will not be changed by any z's around the loop. And the same thing for any x's around a union of such path. But if you apply a loop around something that rotates, that is around the torus, so it's not simply connected, this cannot be written as a product of stabilizers, a product of plaquettes. But it's still, if you can check that if you apply this, a state that after you apply this is still satisfied by all the checks. And the reason is that z's along this commute with all the checks.
I think the term logical operator wasn't defined yet. It's applying Pauli's, but transforms the code word to a code word. So it preserves the code, but it doesn't preserve specific code words. For example, if you apply a loop, a non-contractible loop, then remember the 4 code words that we had, that would transform code words to code words. Actually, for example, if you take a horizontal loop, it would transform it. It's like, never mind. I mean, it transforms code words to code words, but it doesn't preserve specific code words, right? This is a logical operator.
Is this clear? We were going to use this for the entire day. Nati, do you want
No, it's, I mean, the one thing to look at, when you're looking, look at the green loop on the toes there, right? If you're doing such a loop, you essentially don't even know you're on a torus. It's the same situation as in the plane. The new and surprising thing, and this is what Amnon also tried to explain, is here there are contractible means, and excuse me, there is at least one famous topologist in the audience, so bear with me. Contractible means you can, if it's made of rubber, you can shrink it to a point and nothing will happen. Not like this for the 2 main blue loops that you see there. So what's special here, and this is what Amnon explained, is that you get a vanishing even though these are not, they are different. There are loops, but they are not as, they are different from loops in the plane. They are specific to the topology of the torus. Hope this helps.
So should it be clear to us at this point, if we don't know this beforehand, why applying a z over a non-contractible loop preserves the code?
This is something that's very easy. So why applying a z along a non-contractible loop preserves the code follows from the fact that the code, it doesn't preserve the code word, it preserves the code. No, he was talking about non-contractible loops. So why this thing preserves the code, but it doesn't need to preserve a code word. And the reason why it preserves the code, it's because, notice that it does commute with all the stabilizers. So let's just check that it commutes with all the stabilizers. If you have something like this, a z, since it's just a z, it commutes with those stabilizers. Those are made of z's. And it also commutes with stabilizers like this because it intersects them with 2 edges. So x, z, anti-commutes, but 2 times they commute. No. No. Sorry, it doesn't commute with it commutes with all the stabilizers, and it doesn't preserve the code word. It changes the code word. Let's see why. Amnon. Amnon, it's confusing. Don't go there. Let me explain, and then afterwards you say, okay? So if you have no. If you have a loop around the torus, I'm claiming that it could, but I want to write. Don't worry. So you have. I know. I've heard many stories about Semerit. Okay, so. I know, but just I need to explain why the logical code is. I mean, I can avoid explaining this, but it's very simple. First of all, notice that it does commute, and then if it does commute, then a state in the code that after you apply A, which does commute with a state, you want with a stabilizer, you want to know if A psi is still in the code, and so it preserves the eigenspace. So S A of psi, because it commutes, equals A S of psi because it commutes, and then S of psi is in the code, so this is equal to A psi, which means that this too is in the code. It's a torus.
Okay, let's move on. The important point for this is to understand that in order for a logical operation to be performed as a noise, we need some non-contractible loop of Pauli's should happen somehow. As long as we don't have this non-contractible loop, we stay in the same code word. Okay, and as before, the thermal noise just acts with, instead of flips, with Pauli's and under detailed balance. So let's just focus on the Z-checks excitations, which means what happens when some X Pauli X is performed on this on the system. So we see that if we act here with X and here with X, we have only two violations of the V term, here and here. Why this is not violated? Because we have an even number of flips, and because it's a parity product, we have an even number, and this is not violated. And we can take this string and make it longer by applying more Pauli's. And this reminds us of the 1D Ising model, in which we have an error, and enlarging the error results only in two check violations, only point light at the end of the string. In 1D we had a string on 1D, but here we have a 1D string which is embedded in 2D. Is that clear? No?
Yeah.
Okay. So only the checks on the endpoints are triggered. Now we'll do the same procedure of the chain complex for this 2D toric code, and see that if we focus only on the Z-checks, we have the Z-check sitting on plaquettes, and it's a product of the qubits according to the delta 2 boundary. And the X checks, which we'll talk about in the next slide, we disregard. So we see that the Z checks and the qubits are actually a two-level chain. So even though we have 3 spaces and we sit in 2 dimensions, the walls, the Z checks and the qubit sits in the spaces such that they create only a 2-level chain, and because of this, violations are point-like. Okay? And the same happens with the X checks, but with the co-boundary. X checks live on the vertices, and we create again strings, and we pay only with the boundaries of the string, which are the triggered X checks. And again, we have a 2-level chain. How much time do I have?
I think minus 7.
I think minus, but effectively.
Effectively, so would 5 minutes be good to finish the?
Let's try. I will rush it, but okay.
I don't know really what's the time. How are we doing in terms of stamina?
I think low.
Okay, the
No,
lecture
not
is
for me,
low.
for them.
Okay, let's 7 minutes.
Okay, we'll make it. Okay, so we can also see in this chain complex, when we put the Z checks like this and X checks like this, that the fact we made the walls like this, that we have 2 spaces between the 2 types of checks. This gives us the, it can be shown that this gives us the commutation of the 2 check types. And we got for each check type 2-level chain, and because of this, the excitation of each type are strings, and we pay only for the boundaries of the strings, which are point-like. So that's, here is the important point. That's the same problem that we had. So I will say a sentence about a failure. Because we have these boundaries, these violated checks with the same energetic price as in the 1D Ising model, and moving them does not cost us any energy, okay, because we don't care if this sits here or there. The violation will do random walk as they did in the 1D Ising model. And eventually, because we'll have again many strings in a large system as we had in the 1D Ising model, they will meet each other, and after some time, which does not depend on the system size, we'll get a non-contractible loop, and we'll move to a different code wall.
Do you know the real answer? It will depend on the system size, right? But
It
weekly.
will be about the same argument as we had in the 1D Ising model. We have in a large system many such strings, and once all of them meet each other with typical distance, we get an error, a logical error.
So the memory time of the toric
If you take the subtleties, it will be, I think, logarithmic with L. But essentially, it's the same mechanism. So if we want to use the same mechanism of the 2D Ising model, we don't want to have point-like excitation. We want the cost to be to grow with the error, so we want to have loops. How can we get such a thing? We just need to add more vector spaces, we add here another space and we get the meta x checks like we had in the 2D Ising model. But here the problem is that we need to add a space for each type of checks. So we need to add another one for the z checks. Now we take this chain complex and we need to embed it in Euclidean space. So this results in a 4D toric code, where now checks sit on cube and x checks sit on edges, qubits sit on plaquettes, and instead of having non-contractible 1D loops, we have closed manifolds. The geometry of the 4D toric code is complicated, but it's not very important for the point. The point is that once we do it like this and we get effectively a 2-chain for each check type, we get violations that are a loop for each sector. And as in the 2D Ising model, watch this. As in the 2D Ising model, the same argument will be relevant. The commutation of checks lets us to treat each check sector, the x checks and z checks, as independent classical Markov processes, and the same argument as in the 2D Ising model would be relevant. Even though we're embedded in much higher dimension, the loop argument is the same. Questions? Because it's
But it's
very
still
important.
just X and Z checks.
Yes.
So you don't add new checks.
No, that's the point. I'm not changing the Hamiltonian, I'm just adding more spaces. And this changes where the checks sit and create the geometrical constraint, which makes the violations loops. Yes. Gilad. There's a question.
So kind of a general question. You're talking about self-correcting memory. When I have a code, classical or quantum, and I want to say what the distance is, I just need to know about the ground state, right? And I can get the same code with different Hamiltonians and have the same distance. Like the 1D and 2D Ising model have the same ground state manifold. But in terms of self-correction, it seems like it depends on what the Hamiltonian is, right?
I'm not sure I understand the question.
So I guess the question is there some code in the sense of just ground state manifold where you know that it's self-correcting for any Hamiltonian that has that ground state manifold?
I don't know. We can talk about it later.
But just to say, later in Tali's talk, you will refer to this. I mean, different Hamiltonians correspond to addition. I mean, you can add, by changing the Hamiltonian, many more checks, and that will increase the robustness.
So, and this again is self-correcting only under critical temperature, which would be different because the lattice is different and you have a different factor.
Can you explain the picture?
It's only an illustration because it should be 4D and yes. But the idea is that we have some error manifold which has a boundary and it sits in a higher dimension, and we pay the cost of the loop, which is the boundary of the error. Okay, before we had a 2D error in 2D, now we have a 2D error sitting in a higher dimension.
Now, whether this loop is contractible or not is an issue or not?
Yes.
It is contractible.
Yes, Yes, it's an error. And because of the energetics, it will shrink generally. As in the 2D Ising model. The toric code? No. No. In the 2D toric code, the error was a string, and the boundaries were points. Here, the error is a manifold, and the boundary is a loop. Okay. I will
Boundary
finish.
meaning where the energy is not zero.
A small practical question. I know that the surface code is usually preferred because physical constraints, architectures of qubits, they usually sit on a grid. Do you know of any physical implementation of quantum hardware that would support 4D torus cord?
I don't know. Dorit, maybe you know?
No. Yeah, but one of the biggest question in the field is really making self-correction in low dimensions so that it is actually implementable.
I'm a physicist, so I don't really know everything about this, but you seem to have the problem of non-contractible loops because you use the toric codes. Are there non-toric codes where you don't have to have higher dimensions to have contractible loops only?
So I don't know. It's a specific argument about the toric code. I don't know how to generalize this. Okay, so just to conclude, we saw that the stability or the ability to retain memory comes from the geometry of excitations, and not that's the main point, and not the dimensions we sit in. So it's not like an argument of if you have a higher dimension, it's just better. It's the higher dimension. It's what lets us to get two things. One is to get additional vector spaces that create the geometry in which we have a macroscopic excitation cost, and also the ability to have the local checks commute. We saw that the 2D toric code has point-like excitation, and because of that, in the same argument as in the 1D Ising, we don't have self-correction. And in the 4D case, we do have loop excitation thanks to the meta checks in both sectors, and energy grows with loop length. And in summary, geometry dictates the energy. Bitted balance is the one that connects this energy landscape and the energy cost to the dynamics. And the memory time is controlled by the free energy barrier. In the 2D toric code, we have point violations and no self-correction. In the 4D toric code, we get the loop violations and self-correction below the critical temperature.
Okay, I think there are no urgent questions, and there are urgent dates and nuts for Tu B'Shvat.